Alison has very kindly come along tonight to talk to us about FreeDV, so our digital HF mode. So welcome and thank you.
Right, thank you, Simon. Right, first question is, how many of you have been using digital modes? Quite a fair portion. Now these all on the VHF bands?
UHF and VHF.
Yeah, okay. Yeah, okay. Now, how many of you use data on HF? Okay. Now you can do all kinds of stuff on that, can't you? Have you ever used voice via data on HF? It's got two.
Rarely use voice at all, any mode.
There's a couple of people actually do. What have you actually used?
That, once.
Once, okay. Right.
Drove me around the bend.
Okay, right. Well, we'll introduce you a little bit to FreeDV tonight, just give you a little bit about what you need and a little bit on the technical side. I'm not going to go too deep because we haven't got that much time tonight, but I'll get through most of it, and then we'll do a couple of video files. One is how it was about 12 months ago, and one is to how it's been improved up to now. Okay, so now this is continuously under development, and the software is changing all the time, but you guys as radio amateurs have access to the code, and you are invited to actually try and make improvements yourself, okay, and to actually try them out. Now it's good to have a play with because there's lots of things we can actually do with it. One, we can actually send voice on it. The other is we can send our station ID. The other is we can send data on various modes. So it can be quite a useful device to combine data and voice together. You know, where else does this sort of thing get used? Well, commercially, we use it for things like shipping, where we have voice and data transmitted. Military use it a lot, but not FreeDV, a different type of it, which I'll explain a little bit later. So it has great advantages over SSB, because when you're listening to single sideband, what you're listening to? You're listening to a load of mush, aren't you? Now, one of the beauties about the digital comms, and those people that do use digital, is you can decode things right down into the noise, where you can't hear normal speech. So that's where it has a great advantage. It also means that if you get the setup right, and all your matching and everything done, then it can actually sound more like an FM signal, which is extremely good. Now, if you're used to using digital on VHF, you will recognise a little bit of the digitization on this as we actually go through. So, amateur radio is now converting and switching to digital. Is it a fad? Is it going to be here for a long time? We don't know yet. We'll have to wait and see. Particularly the VHF and UHF stuff is likely to settle on one standard at some point or other, perhaps within the next 5 years. But for now, it's going through a transition period, much as we went through a transition period going from sort of AM to SSB, or even going from CW to digital modes. So this is basically going on and on and on. It's natural progression. FreeDV, which is the software where it's called, and it's called Free Digital Voice because it's absolutely, totally open source for you. You can do what you want with it. All the source files are available on the website at freedv.com. You can download them, you can edit them, you can try them, you can experiment, which is exactly what amateur radio is all about. There is nothing proprietary in it in any shape or form. Now, what's in it as such? Well, first of all, I'm going to come around this side. We have codec 2, which is what the whole thing is based around. We have our A to D converter. We then encode it. We have our forward error correction on encode. We go to our modulator, which then feeds into the HF or VHF radio. On receive, we have demod, we have the error correction, we have the decoder in codec 2, and then we have the D2A to convert it back to audio, which can be fed into your receiver's filtering system or into some external AF amplifier come speaker. Or if you use a desktop software, then that will obviously come out of your sound card accordingly. Now, you probably say, well, how much bandwidth does this actually use on HF? Well, the maximum bandwidth it uses is 1.25 kilohertz. So it's basically roughly half that of SSB. So that's a good space saving as far as spectrum is actually concerned. It basically sort of, on the 1600 bits per second setting, we have in there 25 bits of text for your call sign ID, 300 bits for forward error correction, 16 times 50 baud QPSK carriers, and differential QPSK demodulation as well. When we go down to 700 baud, and I'll come to why we use 700 baud in a minute, we have 650 bits per second for voice encoding, 50 bits, no forward error correction because it's not needed at the lower data rate, and there's 14 75 baud QPSK carriers. Now, one of the things it also has on the lower bit rate is frequency diversion, frequency sort of diversity, which is actually used to combat fading and sort of slight drift on some radios, which happens so as it can resynchronize itself and keep itself in lock. It looks quite a technical piece of kit, but there's actually not that much to it because they are made into little boards. Now, when I first showed you the earlier slide, that piece of kit, that is a complete piece, and on there you have your AF input, your PTT, and obviously your speaker output. You also have your ability to program, your DC power. It has internal speaker and internal microphone. It can be actually quite useful on your desktop, and it has extremely good sound reproduction. The alternate bit is you can have little boards, PCB boards like these. This will allow you to actually load your software, modify it, do your bits and pieces, and actually interface it to your own radio. So if you wanted to go internal, if you're that technically minded, you can actually you can do. So these boards are available.
So I take it like that, Alison, that you don't need too much processing power to do the encoding and decoding.
Not too much, no. Not on the amateur radio versions anyway. Okay. So, one of the other beauties about this, using this particular FreeDV mode, is there's no interleaving time. So basically sort of there's very low latency on the actual signal. It's very fast in synchronization, and it basically sort of, if you get extreme fading, it's very quick actually recovery on it as well. So let's just go back a little bit. It was all based around the codec 2. The software or firmware is written open source. The original was 3200 to 1200 bits per second. It was speech only, and digital radio applications are expected in the not too distant future. The mission for the development of getting FreeDV into amateur radio is to provide a digital interface similar to the VHF stuff that you're actually been using more recently, But on HF, we do make sort of the digital sound much better than the actual sort of analog. So you get rid of a lot of the mush. It works great over all HF channels from top band right up to 30 megs. It has negative channel signal to noise ratios, and I'll come to more of that in a bit. This is actually hard to do in the main software, but it has been accomplished. In the analog radio, the analog signal has lots of redundancy. Okay, and what we mean by redundancy, you have quite a broad spectrum of sound which is transmitted over the carrier, which, as you know, is between 300 and 2.8 kilohertz, or 3 kilohertz if you want, or the new HF standard, which is 2.4 kilohertz. So there's lots of sound there, and if a little bit of the top edge of, say, the audio gets sort of battered a little bit by interference, then you can always hear the lower bits and you can still decode it. Digital has some global bits as well, where some bits are more significant than the others. So different bits have different importance. For instance, the higher bits, if you lose a little one of those bits, you will totally lose the whole signal. If you lose one of the lower bits, then you don't lose it, and you can just literally carry on. Memory, error propagation. One of the problems that happens in digital, and I know you experience this on the VHF bands as well, is if you do get a little bit of dropout, it takes a second or so before it re-establishes its communication again. Exactly the same thing is happening on HF. So what it will do, if it misses one bit, it will miss the second bit, and then it will effectively resync again. So that's the memory part, where it misses the first bit, misses the second, and then basically will resync on the third. So that's where it helps sort of correct its errors, so to speak. With normal voice, gradual decrease in the quality of signal to noise. The more noise on the band you get, the less intelligible the actual audio signal becomes. So the more mush you get, the harder and harder, and the more interference, maybe from your VDSL or whatever, you also have great difficulty in actual sort of being able to understand the voice. Analog applies power intelligently. What do we mean by this? Well, basically it's over quite a spectrum, and this just reconfirms what I said a few moments ago, that if you lose a little bit, you hear it, and then you say, yes, but I can understand and predict what's going to be said, because I'm used to hearing the human voice. So we don't have to sort of guess on anything. With digital, the power is distributed in frequency and time, so it's spread evenly across the lot, whereas basically the analog will be up and down depending upon the frequency. So, in bad HF channels, in other words, lots of interference, and using an analog signal, if communications gets very bad, you repeat yourself, don't you? You use phonetics. So for instance, you will hear something and you will automatically and naturally start saying it twice, or you will, instead of saying G8ROG, you'll go Golf 8 Romeo's Golf, or whatever your particular call sign is, but the message gets through. This is like lowering the bit rate on the actual digital signal. The slower it is, the easier it is for the actual signal to get through. So we're allocating more power to each letter if we repeat ourselves. So if we go G, it's only tiny. If we go golf, it's longer, so you're putting more power out for that particular letter or ID. And this is called human forward error correction, in simple terms. The digital equivalent, we lower the codec bitrate, which lowers the speech quality to the edge of intelligibility. Okay, if it does get that bad, we do repeat ourselves, so it's okay to repeat ourselves as we did in analog. It's okay if speech quality is low. We can still predict what is actually going to be said. The lower bit rate means we actually transmit more power on a particular digit, whereas if we increase the bit rate, we use less power per bit. So the lower the bit rate, the better chance of actually getting through. The standards which have been applied for amateur radio use at the moment are 700 bits per second or 1200 bits per second. These are the two which have basically sort of been agreed as will be the starting points for the actual main experiments and development. It also means they're away from the commercial standards, which means that there's no conflict with anything else on shared bands. So that's what we've actually used for that one. Now, yes, there are other bit rates we can use. When it was first started, it was started with 1600 bits per second, but that was quickly found on amateur radio that most people couldn't cope with it. It needed too much stability on your actual radio, and it also sort of meant people had difficulty in actually hearing it because of the interference coming from adjacent channels sort of knocked the bits out, and unfortunately sort of kept making it go out of sync. With 700 bits and 1200 bits, the interference is much, much less. We've been transmitting the GB2RS news bulletin now for quite some time on the 700 bits per second system, and basically sort of it's proving quite successful, particularly in the south of England where the analog signal pretty well disappears into the noise. The digital one is actually getting through, which is brilliant. Now, if all goes well, I'll play you a file here of how it used to be when we first started.
So let's record a little for the club talk I'm giving this week. That's the Fairfield Amateur Radio Association. So we can do a little demonstration of what digital voice sounds like. Back to you, Andy. In Mississippi, this is K5MVP. This is AA6E.
AA6E, K5 Mike Victor Peter, K5 most valuable player on the Gulf Coast of Mississippi. Fine, Marty. Excellent signal and the flexo sounding is beautiful on digital. Like your THS, you're Mississippi, 30 miles west of Biloxi. And this is the anniversary of Katrina 10 years ago. And Katrina made landfall right in this county. And so it's a beautiful day, thank goodness, and we don't have a hurricane to worry about overwatching them out on the Gulf in the Atlantic right now to make sure. Anyway, Marty, the equipment here is the new little blue box by a lot of good fellows who put it together, the SM1000, and we've had it for about 2 weeks. And it's driving a Collins KWM2 and a 40L1. So back to you, Marty, K5 Mike Victor Peter.
Okay, Andy, thank you very much for the equipment rundown. I am running the Flex 6500 here with a built-in sort of plug-in to handle FreeDV, free digital voice. And not using my amp. I do have an SB220 amp, which I have used at times to get through when band conditions aren't too good, but today seems to be fine. Getting about, I think, 80% decode on you right now, and there's QSB that we can see in the trace. And when it dips down, then we lose your signal for a few seconds, but nothing bad. And I don't know how we demonstrate digital except by doing it and demonstrating how what the signal noise ratio is and the fidelity and so on. At times very impressive, and the bandwidth required is so small. It's only I think it's 1.25 kilohertz, a lot less than a sideband signal. The downside though is that you do need a fairly good signal to noise ratio. I'm not sure exactly. Well, we're doing pretty well today. We're doing okay on 20 meters this afternoon. So back to you, Andy, K5 MVP. This is AA6E.
Okay, Marty. AA6E, K5, Mike Victor Peter on the Gulf Coast of Mississippi. And that was a beautiful transmission, Marty. Didn't miss a thing. I had a phone call. My wife called me, and but I missed a little bit of that just because of the phone call. And we're on 71, rather on 14150, and the upper sideband digital signal is at 800 to 1200 cycles. So we're on 71, 800 to 71, 14150.8 to 14150 1.2. And so the signals are much better down here because a lot of folks don't realize that 14230 is slow scan, 14233 is digital slow scan, and 14236 is digital audio. Well, we're having a lot of fun with it, just brand new with it, and always wanted to play with it. And we're having a lot of fun meeting everyone, and it's a nice group of people. So back to you, Marty. Won't hold it too long because I have to get lunch ready. That was the phone call saying we need to get lunch ready because she's out shopping right now. Anyway, back to you, Marty. Won't hold it long. AA6 Echo, K5 Mike Victor Peter, Mississippi on the Gulf Coast.
Very good, Andy, and thank you very much for the short contact, and hope we can talk again soon. K5 MVP, this is AA6E, let's say 73s, and good afternoon.
Okay, Marty, and just was curious, did you get a good recording?
Well, I'm just going to try it right now. I think I did. It looks all right to me anyway, and you never know. And if I'll probably put it on YouTube and send you a link if it works out. This is AA6E, and I'll be clear, 73.
Okay, Marty. Did you want me to go to single sideband to show the difference?
Well, sure, let's do that. I can switch the same frequency. I guess we're legal on 150, just barely, with our upper sideband. So we'll change modes to upper sideband.
Okay, let me make a quick switch here. K5 Mike Victor Peter, changing from digital to single sideband.
Didn't have the SSB plugged in just right here. Anyway, this is the single sideband signal, and running a little more power, not much, but this is SSB from the KWM2. So Marty, how do you copy K5 Mike Victor Peter?
K5 Mike Victor Peter, this is AA6E, fine copy, but obviously it's a different thing. Let's see if I can get my audio in the right level here. You clearly, it's a different thing when you have sideband, but it's a very good demonstration of where we are. I've got some feedback, RF feedback in my recording loop here, which may be audible, but I think we've made the point here. So thank you very much for this little trial.
So let's see what it sounds like now, and with the improvements. The other one was over 12 months ago. This one is very recent.
Over what path? How long was the path between the two stations?
I believe it was about 1,000 kilometres,
Right,
but don't hold me for that. Check up the call signs in your call book.
You could never tell whether an AA6 is California or any other state.
I think one of them said he was in Florida or something.
Was it? No.
Florida, no, was that
Mississippi. It's a long way.
Yeah.
The improvements they've made, Alison, what sort of improvements have improved the quality?
It's mainly been in the way in which the sort of digital signal is decoded. So all the forward error corrections have been improved. There's also been great improvement on monitoring the actual quality of the actual digital sound and then automatically logging in to make corrections on it. Now,
K0.
you
I'm located near Tampa, Florida. We're using open source FreeDV with codec 2. The bandwidth on this mode is about 1.1 kilohertz. We're going to make a test here now. We're switching from digital FreeDV to analog sideband. Oops, stand by. It's for DVR. Okay, this is M4DVR doing the analog mode now. Just to give you an idea here of how much difference there is between sideband and digital. Okay, back to digital. Okay, the codec and modem was developed by David Rowe. Graphics user interface by Dave Whitten. Back to you, Mel. K0PFX in for DVR.
okay?
So Alison, is it high duty cycle in the same way that, say, a PSK signal would be?
Right, I was actually just coming back to that one in just 1 second.
It looked like almost the carrier strength was independent of the audio.
Yeah. There's phase shifted carriers basically.
Yeah.
There's 75 Hz carriers across the bandwidth.
It's 100% duty cycle,
Yes.
isn't it?
Yeah.
It is.
Which is a problem.
So,
I could only use it on 25 watts.
Yeah, and the
Right, now, first of all, basically sort of one of the biggest mistakes a lot of people do is when they use digital is they put the sort of modulation into the transmitter and they wind it right up to full power. With digital modes you only need approximately 25 to 33% of the actual normal audio. So if you've got an actual 100 watt transmitter, then really you should not be exceeding 30 watts when you're actually using sort of digital modes, okay? Because if you do, then what will happen is your heat sinks start getting extremely hot because you exceed the rating of the radio, and in addition to that, you also start putting splatter out on the bands because you tend to be overdriving the radio and causing all kinds of problems in the PA stage and things like that. So it's not good to run your digital modes above about 25 to 30% of what the rated power is for normal SSB. Okay? So as long as you that's what I was looking for. So as long as you actually sort of keep to that sort of level, you'll be absolutely fine. Now, as you heard on those transmissions on the sound the AV files, they were only using about 20% of the rating of the actual radio in SSB mode. So you don't need much power at all to be able to get the digital voice actually through. so it has quite a good recovery rate. And unfortunately, one of the files I was going to show you was one where there's a lot of cold channel interference on, but I didn't find it in time for tonight. Where basically, particularly if there's a contest on, you know how difficult it is to actually sort of try and hear anything on the band, or try and squeeze in between two stations. Well, you can do that with this without much problems, and you don't hear all the clutter from the others. You don't hear all that interference and mush you get off the normal single sideband analog signal. You just get, as you heard on relatively clear audio, which is actually what you actually want to achieve. So it's always good to experiment with digital voice. There are plenty of nets in the UK now operating on digital voice up and down the UK. There is a software version, a desktop software version.
Are you saying that there was a piece of kit on the market that you can just plug in next to your transceiver, or are you showing the circuit?
You just plug a mic into your laptop and it runs the software on your laptop.
Yeah, you plug in a circuit. Yeah, okay. So I used the software on the laptop, and of course that was quite a problem setting it up.
If you didn't want to start going through computers and such like, is there somewhere in the UK that sells equipment for doing digital HF?
Yes, you can speak to me. You asked. It's, right.